AP1 Momentum Multiple Choice Set 2. There's another video where I have a 1 here, but it is incorrect. It has the same color card, and it starts with, I think, 1 and 2 and 4 and something like that. So I think I have that mislabeled. This is definitely should be set 2. Because we're talking about collisions, and that's usually the second half of the momentum unit, is collisions. So we have in a one-dimensional, perfectly elastic collision. So this is, I think, the first time we've run across one of these. An object of mass m is traveling with the speed VO in the positive x direction when it strikes an object with a mass 3m that is at rest. So we have an object of a single mass moving with a speed called VO, and it hits an object 3 times as massive who's at rest. What are the object's velocities following the collision? Alright, so here's what's got to happen. This, because it's elastic, there is a kinetic energy is conserved. The problem is also going to be a little trickier. I'm not going to lie. So let's take a look at it. So I have before, or initially, and after. And before, the momentum is all in the form of the little object. It's single mass times VO. And that has to equal the momentum afterwards. Now afterwards you have 2 objects. You have the momentum and the final velocity of the little guy. So we'll say small, right? Plus the momentum of the other one, which is 3m. He's 3 times the mass, and its final velocity of the large. Because now, after the little guy hits him, he could be moving. So there's probably momentum in both of these. And it has to equal this momentum here. Problem is, there's a lot of unknowns. I don't know how fast either one of them are going afterwards. All I know really the masses and how fast this one's going initially. If you look at it. But since it's elastic, I also know that kinetic energy is conserved. And that means that 1/2 mVo squared equals, well, 1/2 mv final of the small squared plus 1/2 3m v final of the larger one squared. So I actually have 2 equations to work with, so I can handle the extra variables. So remember, we're treating this as a known, right? VO. And obviously the masses is a known. And they were asking us for the velocities following the collision of both of them, right? Okay. So let's do this. Let's solve this equation for one of these 2. Let's solve it for v final of the small. So I'm going to subtract this from both sides. So we're going to pick up with this. I'll make sure we're clear. We're going to start with mvo equals mv final of the small plus 3m v final of the large. And I'm going to solve for v final small. So it's going to be m, well, the m's divide out of everybody, right? Gone. So that means v final small equals VO minus 3v final large. If I bring that over, yeah, it should be, alright. So I now have the final velocity of the small object by itself, and I can replace that in here. Yeah, I know, there's a square there. And I can go through and then solve for the final velocity of the large. So let's give it a shot. I have 1/2 mVo squared equals 1/2 m. I'm going to replace this with this. VO minus 3v final squared plus 1/2 3m v final large squared. All right, well, some of this is definitely going to go away. The halves are all gone. M's are all gone. So I really have VO squared equals, I got to square this monster. So that's going to be VO squared minus 6 VO V final large. And then this squared, so that's plus 9 V final large squared. So I just did FOIL on this thing. Plus a V final large squared. No, and a 3 there too. There we go. All right. Well, let's simplify this thing. We can combine these two. That's 9 of these plus another 3. So that's 9, 10, 11, 12. So I have 12 V final large squareds. I have this one right here, which is negative 6 VO V final large. And if I subtract VO from both sides, VO squared, they actually go away. So I have 0 equals this garbage. All right. Not too bad. It's good that that went away because now we don't have to use a quadratic formula. I can factor a V final large out of both of these. And for that matter, I could factor a 6 as well. Do I want to? Well, why not? So 6 times V final large times 2 V final large minus 1. VO, minus VO. There it is. I almost lost my VO. Equals 0. All right, so your options here are either this equals 0, in other words, either V final large equals 0, that's one option, or this whole thing equals 0. Because this times this is equal to 0, so one of them's got to be. So let's set this equal to 0 and see what we get. 2V final large minus VO equals 0. That means 2V final large equals, I'm running out of space here on you. All right, equals VO divided by 2. So the other option is that V final large equals VO divided by 2. So I'm going to guess there's two possibilities. I'm guessing this one doesn't happen. I'm going to guess that this is the one we want to use, that the final velocity of the large is half of the original velocity. So now I got to go back and plug that in. So I think, if I've done the algebra right, that I now know that V final large is equal to half of the original velocity before they collided. I'm going to use, I think it's a simpler equation without the squares. I think I'm going to use this and plug this back in for V final large. So I'm going to write MVO equals MV final small plus 3M times VO divided by 2. So I replaced the VO, I replaced this with what I think I figured out it was earlier. And I end up with this. Now the M's go away again, so I have VO equals V final small plus 3, well, the M's go away, VO over 2. And I'm looking for V final small, so I'm going to subtract this from both sides. I have VO minus 3 over 2 VO equals V final small. That's 1.5, so that's a negative half. Negative VO divided by 2, is that right? Because this is 2 over 2. Negative 1/2, yeah. So interestingly enough, I have them as having the same velocity. That's interesting. I wonder, the other option is to plug in 0, which means that the little guy would bounce back with the same velocity that it had. And that's a possibility if they get extremely enough larger. Like if it was 50 times larger, I would say the big one's not really moving, the little one's going to bounce back. But they're only, still, I'm going to go with this for now. And let's see how well I did. See if I made any mistake, where I made mistakes. So the small one, I have as half in the negative x, going backwards. And the other one, the large one, is half in the positive x. So I have there, my answer is there, it's D. Now the question is it correct? What number is this? Number 20. 20, the answer is D. So I got lucky on that one. Now my paperwork was everywhere, so I may have to redo that one. If you're watching that and you're like, well, when half the time you're writing, you weren't even like seen, could you redo that one? Please send me a message and I will. But what this is letting us know is this. Elastic collisions are algebraically more complicated because you have two velocities initially. So you have, well, you could have two initially if they're both moving, and you could have two different ones afterwards. So you have so many unknowns when there's elastic, and the only way to handle it is to utilize the fact that kinetic energy is conserved, which is great, but then you got to solve in multiple equations and do a lot of substitutions, and there's a lot of places to make mistakes. So it's much more algebraically challenging with elastic collisions. Open cart in a level surface is rolling without frictional loss through a vertical downpour of rain. So none of these, the vertical forces on this, are going to affect the horizontal momentum. They're going to be canceled out by the normal force. So all this is going to do is add to the mass. But the conservation of momentum has to hold. So as the mass goes up, the velocity should go down. Let's see what they ask, though. As the cart rolls, an appreciable amount of rainwater accumulates in the cart. The speed of the cart will increase, no. Increase, no. Decrease, yes. Conservation of momentum. It has to keep the same value that it had before. So maybe when it didn't have much mass, it was, 2 kilograms times 5 meters per second. Great. That'd be 10. As mass increases, if the mass goes up to 10 kilograms, then the speed's got to drop down to 1 to keep the same momentum. So I would say that. 21, and that is C is correct, yes. I haven't been putting my numbers up here. 27. I think we've seen this question as in energy form, or maybe earlier, I can't remember exactly, but we got a force applied for amount of time, so that's impulse right there. The area in here, without even reading what they're asking, if I have a force of 5 newtons applied for 1 second, that is impulse, right? Force times time. So that is the change of momentum. So let's say 2 blocks of mass M and 2M are initially at rest on a force of F is individually, so this is done to both of them. The graph shows how F varies with time. Basically, it's just given out in 1 second. Which block has the greater average power delivered to them? So we really need, power is more energy. So we need to find their final velocities. And I think we can now use, I think in the earlier version of this, we had to use some kinematics and stuff, but we can use impulse now. So the initial momentum, they're both at rest, so their initial momentum is 0. Their final momentum, which is their change in momentum, is going to be 5 times 1 second. That's going to be the impulse. 5 Newton seconds, or it's also kilogram meters per second. And that's for both of them. They both experience the same change in momentum because they both experience the same force for that same 1 second. But this guy, the little guy, that means that his final momentum is 5 ns equals his mass, which is a single m, times his velocity of the little one. Notice the starting momentum was 0, so the change in momentum is just whatever they ended up with. For the larger guy, that 5 Newton seconds is equal to 2m. Well, I said little, I'll go small. Velocity of large. So, let's see. Well, the masses are going to go away. Well, no, not necessarily, actually. But the block, now the one that'll have the most power. So let's see. This means, let's go with velocity. So this velocity of the small one is 5 over m. Velocity of the large one is 5 over 2m. Now, power would be the change in kinetic energy. So they both started at rest. So the little one's kinetic energy is going to be 1/2 m this squared. The kinetic energy of this one is going to be 1/2 2m times this. It's new velocity, the velocity we figured, squared. Alright, so this gives me a 25 here, this m squared here, which is going to cancel one of these, and a 2 in the bottom. So I'm going to have, if I can squeeze this in here, we'll just do it right underneath here. I'm going to have 25 in the top, along with a 2m in the bottom. Alright, that'll be the change in kinetic energy. This was going to be, so 25, and you're going to have a 4m squared, so that's going to still leave us an m in the bottom. You get a 4 here, another 2 in the bottom, that's actually 8, so that's going to be a 2 in the top, so that's going to be a 4 in the bottom, so 4 in the bottom, and 25 up here. So this is a smaller change in kinetic energy. This is a larger change, because this velocity of this kinetic energy here is smaller. But in fact, it's half, because there's a bigger number in the bottom, 4. Power just means time, but they say over the 3 seconds, but the only really time it happened was over 1 second. So this, the amount of time is the same for both. So this happened in 1 second, and this happened in 1 second, so the power delivered is more for this one, for the little guy. He has a bigger change in kinetic energy. 27, yeah. So we use impulse to get an expression for the velocity of each. And then we use those velocities in kinetic energy to see which one has the bigger change in kinetic energy. Whichever one has that bigger change in kinetic energy had more work done, had a greater rate of power. Stationary object explodes, breaking into 3 pieces. Masses, 3 pieces of masses. Is that? I'm not even sure what this means. Right here. Breaking into 3 masses. I'm assuming that's an M. M, and 3m. The two pieces of mass m move off at right angles to each other with the same magnitude of momentum mv. So they have the same speed, same, okay. What are the magnitude and direction of the velocity of the third piece having the mass? Okay, so remember that vector stuff we did earlier? It was stationary. All these vectors, this one, and the third one we're about to draw in here, they have to add up to 0. So if I draw these two, their resultant is this. And to cancel, the third piece must have a momentum that is that big and in that direction. Now the direction is clearly one of these. Here, here, here. It's one of those three. How about the magnitude? Well, you need really the length of this arrow, but that's just Pythagorean theorem, and this is 45, 45. So these two sides are the same. All you really need to do is do mv squared plus mv squared, the whole thing, by the way, each side squared, and take the square root. You can do Pythagorean theorem. Or you could remember that it's going to be the square root of 2 times this. So one of the things you're supposed to know in this world is if you have a triangle, right triangle, with the two legs are the same, if you know this is mv or anything else, this hypotenuse is going to be mv times the square root of 2. It's a thing. You can see it right here, by the way. If you add these up, you get 2 times mv squared. Well, if you take the square root of mv squared, you just get mv, so it's mv times the square root of 2. Boom. So, I need one. Now, they want to know the velocity of the piece having 3m. This is just, I know its momentum for the third piece is mv. Actually, I should take back its, is it mv? Yeah, it's mv square root of 2 is its momentum, but that would be, it's 3 times bigger, 3m times its final velocity. So I'm solving for the velocity. So don't forget, this is equal to its momentum, but it also is equal to this because it's got its mass and it's moving at some velocity. So I got to divide by 3m. So the m's are going to go away. I'm going to have, I guess we'll look at it as square root of 2 over 3 times v is equal to v final. I would go with that. D. 28. D. So certainly you should get it down to one of these three. This I could understand if you forgot to set it equal to the momentum over here. If you just said, oh, there it is. And somehow, said, oh, forget the mass and just wrote, yeah, I could see that. But this would be, here's what it needs to be based on what the vectors tell me. And of course, this is what it's going to be based on its mass times velocity. But the directions should eliminate a couple of these. And I would point out that, using logic, if the directions, these two directions are wrong, but they give this answer for one of them and our correct answer, this is the one you definitely want to rule out. Right? Because it gives you what you know is the right direction, but it doesn't have a wrong direction to go with it. So, I don't know. Logically, you could probably boil it down to one of these two. 29. The two blocks of masses m and 2m shown above initially travel the same speed v, but in opposite directions. They collide and stick together. How much mechanical energy is lost? So first thing we need to do is figure out what their velocity is going to be afterwards. So their initial momentum is going to be, we'll assume this way is positive. So this guy is going to have mv. This one's going to have negative 2mv. v. That's their initial momentum. After they collide, they stick together. So they are now an object with total mass of 3m, and I need this final velocity. Well, this is going to be just negative mv equals 3m times v final. So m's go away. I'll divide by 3. So the final velocity is a third of what their original velocities, remember they're the same one, is. And it's going this way. Well, not a surprise. This has more mass. It's more momentum that way. Now, that's just the velocity. We need to figure out the kinetic energy in beginning and the end. So in the beginning, ready? We're going to do this on a little bit of a separate piece of paper. All right. So for kinetic energy, initial, we've got 1/2 mv squared. That's the kinetic energy of this guy. Plus, not minus, direction doesn't matter for kinetic energy, 1/2 2m v squared. The kinetic energy final is going to be 1/2 3m, because that's a mass, times this velocity that we found squared. And we can drop the negative. So we can just say v over 3 squared. So here's our initial kinetic energy. Here's our final. The direction doesn't matter for kinetic energy, so that's why we write that plus there. So this is going to be a half. This is really going to come down to 1 mv squared plus half. So this is 3/2 mv squared. Over here, I'm going to end up with, let's see, well, this is going to be a 9. So it's going to be a 3 after this one cancels. Then it's going to be a 2. So it's going to be a 6 in the bottom, v squared, and an m in the top. I think if I do that right. Okay. They want to know what's the change. How much mechanical energy is lost. So we want to know what's the change here. So if I do, they're both mv squared. So if I do 3 over 2 mv squareds minus mv squared over 6, well, let's see, I'm going to have to multiply top and bottom by 3 to get a common denominator. So it's 9 mv squared over 6 minus an mv squared over 6 gives me 8 mv squareds over 6, which I can reduce 4/3 mv squared. So I would go with this. Let's see if it's one of the answers. There we go. I would say D would be the answer then. All right, so if it goes, you have to find this. The steps are you got to use conservation of momentum to find the final velocity after they stick together. Then you got to go and figure out their initial kinetic energy, that disregards direction, and their final kinetic energy using that velocity you just found. Get them, and then subtract them to see how much you lost. In this case, I got 4/3 that, and number 29 is in fact D. So yes, I'm on a roll. 30. Two objects of mass 0.2 and 0.1 kilograms respectively are moved parallel, interesting, to the x-axis as shown above. The 0.2 kilogram object overtakes and collides with the 0.1 kilogram object. Immediately after the collision, the y component of the 0.2, so we got angles here, is 1 meter per second upward. What is the y component of the, all right. Okay, so here's what we know. Initially, both of their momentums are horizontal. So if one of them after the collision, this one in this case, has a vertical component to its momentum, since there was no vertical component initially, the other object has to have an equal vertical component in terms of momentum. So if this other one was 0.2, it would have the same speed. But it doesn't have the same speed, but it will have the same momentum. So the 0.2 kilogram object after the collision has a momentum of 0.2 times 1. That means after the collision, the smaller one has to have a vertical component the other direction, because there was no vertical component here. So downward, that is the same size as that. That is, that's just 0.2 equals, but it has a mass of 0.1, so what would its velocity need to be? And so I would divide that by 0.1, and I get 0.02. Am I doing that right? Double check me. After the collision, the y component of the velocity, so this would have a y, so this is definitely its momentum upward. Initially there was not, so there's got to be a downward momentum that is the same. So it's got to be one of these two. Oh, divided by 0.1. That's not, it's going to move it the other way. It's 2. There it is. There we go. Should be A. So I could have gotten a calculator out. 0.2 divided by 0.1 is going to move the decimal to the right and make that 2. So it's going to be moving 2 meters per second, which makes sense. It's smaller, so it'll be moving twice as fast. All right. Except for a little bit of arithmetic. I'm pretty good on that one. That was number 30. And it's A. That's what I got there. Okay, good. All right. My things show that there are more, but I think I broke this up. So we are going to do the rest in another video.